Hello, everyone. We now have a three-part series in talks describing, let's see. I'm sorry, everyone. I'm really sick, and I totally botched this. But why don't I just say today's speaker is Alex Bouchard-Côté, and we encourage questions during the talk. You can either there should be a chat window to the next of your YouTube, or you can tweet at phyloseminar. So Alex does all sorts of amazing stuff. His PhD advisor was the well-known Berkeley statistician Michael Jordan. He skipped doing a postdoc and went straight to a faculty position at UBC, where he is today. And his talk today is entitled Advances in Computational Bayesian Methods. Thanks, Alex, and sorry about that.
Thanks, Eric, for the invitation, and get better. The talk will be first motivated by some applications in single-cell cancer phylogenetics. Then I'll talk a little bit about a Bayesian modeling language called BLANG that we're using for this projects and other projects. And if I have time, I'll talk a little bit about some supporting computational statistics techniques that we implemented in BLANG and are using for phylogenetic inference. The motivation is to understand the evolutionary process within a tumor as a long-term project. So that's a collaboration with Sam Aparicio at the BC Cancer Agency and Saurabh Shah at MSK and the BC Cancer Agency. The data that we're looking at is what's called serial patient-derived xenografts. So we take a tumor and engraft it in an immunosuppressed mouse, and then we serially retransplant it and see how the evolutionary dynamics change in time. And eventually we want to look also at how they change in space. So we have a manuscript in preparation with a student co-supervised, Saurabh Sadhi. And the key thing that we need for this research is basically as an input, we need a phylogeny. So we have all these cancer cells. We want to build a phylogenetic tree on these cells. Each of the leaf of that phylogeny would be an individual cell. And we know from which passage in this serial passage experiment it comes from. And we want to track basically different clades of that tree. Well, we can think about them as subpopulations and how their relative prevalence change over time. So we're to make a long story short, we are going to use these trees to feed into population genetics model. The input, in fact, that we're interested in is a distribution over single-cell phylogenies. Before telling you more about the tree, let me just tell me a little bit more about the data. So the measurements that we're looking at are obtained from direct preparation library, which was developed locally at UBC. But it has the same flavor as this 10x genomics platform that's getting very popular. So the data consists in the range of about 1,000 to 10,000 cells, looking at all the passage together. And it's genome-wide, but the coverage is very low, so less than 1x. Because of such low coverage, basically the point mutation are highly uncertain or missing for actually most of the genomic loci for a given cell. So basically, we want to build trees using copy number data. So you can think a bit about the data as these three plots that I show here. So each row is a cell, and the x-axis is the genomic location. And here, since the data is so sparse, we're binning things, and we're looking at rescaled number of reads in such bins. For now, we're going to assume that copy number profiles have been inferred from that picture. Maybe later we would like to propagate the uncertainty on these copy number profile. But for now, just think about it as a fixed copy number profile as input data. And since the measurement is quite noisy. We want to have uncertainty in our tree estimates, so we're going to opt for a Bayesian phylogenetic inference. And basically, the twist compared to other single-cell phylogenetic methods here is that we want to use these copy number profiles instead of point mutation. So for single-cell phylogenetics, point mutation have been the focus so far. So you can look at these two reviews, for example. So the tricky bit now is that these copy number alterations are fairly complex. So there are many phenomena that we need to consider. So for example, we can have local amplifications that I show in panel A here. And these can be overlapping. There are losses, and there's basically a bunch of combination of those that interact in interesting ways. There are other phenomena, but just this small set is already something quite complex. And what we have is some sort of combinatorial dependencies across the sites. So if we model also each individual loci, there would be a lot of repetition, basically too much dependence that is unmodeled and would lead to tree estimates that are overconfident, basically. On the other hand, if we fully want to model this process, we get into what's called in Bayesian computational statistics a doubly intractable model. So just computing the likelihood for one tree is intractable. And in the long term, we would like to approach this using doubly intractable computational statistics tools. But right now, what we're trying to do is get the project started. We have the data, so we want to move on to get some first result. And we would like to simplify the problem, but still get an approach that is doing full Bayesian inference on this data. So here's what we decided to do. We're going to basically look at the data differently. So we're going to apply a lossy encoding to the data. And with this lossy encoding, we'll have as a consequence is that basically at most 2 sites after this encoding will be dependent. So here's an example of what this encoding is. It's fairly simple. So let's say that each row here is a cell, and each column is a genomic location, a bin of copy number, and the color encode different inferred copy numbers. Okay. So what we're going to do is look at the boundary between 2 neighbor bins and construct an indicator that checks if the copy number is the same or different at each side of the boundary. Okay, so for the first one, white is 0, so there's no change here for these 2 cells at that loci, and there's a change here at these two cells, and no change here. So we're going to do this for all the bin boundaries, and we get then these 0, 1 indicator, and we're going to actually discard the data and only use these as we're going to pretend that we only observe this. Now why do we do this? Because if now we look at this transform data, these traits are almost perfect phylogenes. Okay, so what I mean by this is basically we're not actually observing these there's actually noise in the copy number call, so we're not really observing these binary values. So that's ignoring some source of error. There might also have violation of the infinite site assumption. So copy number will typically occur at different loci in the evolutionary regime we're looking at. But because we're binning the data, we might actually get 2 events in the same bin. And we ignore also a few evolutionary scenarios. So here I'm showing in red the problematic scenarios. They are basically cases where you have a gain and then a loss, and the loss basically deletes the boundaries of the earlier gain. Okay, so there's we enumerated these cases, and we established that there are actually a minority of the paths. So we're going to ignore those and try to build them all so that it's robust on these. The benefit for making all these assumptions is that we get fast algorithms. And in some sense, what I would call this kind of type of approach is we're doing AB without ABC. So if you don't know ABC, I'm just going to talk about it for one slide. So it means approximate Bayesian computation. But basically, the setup is similar to ABC, but a bit different. So we want the probability of a tree given the data, but it's computationally too hard. AB without ABC, basically what we're going to do is we're going to approximate instead the posterior of the tree given a function of the data. And here we're going to be very careful about what this function is. And we're going to take it so that standard MCMC applies. And the advantage is that basically after this first step of re-encoding the data, lots of the practical and theoretical tools, they apply directly to our scenario, our modeling problem. And this is almost like ABC, but with ABC, there's a bit more baggage. So instead, we take an arbitrary F and then use a specialized set of techniques akin to rejection sampling to do the computation. So just some sort of, it's almost being Bayesian, but not quite because we don't use the full data. So just an overview of the tree. So basically, we have, we're going to be robust to these violations, we're going to actually have an emission or error model. So there's two objects. One is the latent perfect traits, X, which we say, okay, they respect the perfect phylogeny, but we allow observation to violate the assumption by having an error mode that molds Y given X. So I'm not going to go over the details, but it's essentially one thing that we want to do is to make the parameters for this error mode site-specific, so that if there's a sort of a systematic violation for one loci because of a loss, for example, then we can explain it away by having high error parameter for that loci. So once we make all these assumptions, then we can actually build a new MCMC move, which is specialized to this model. So use basically the perfect phylogeny assumption. So how does it do it? I will talk in more detail a bit later. But the final result of this new move is that if we look at the computational cost for one move in terms of the number of cells and number of loci, for many typical MCMC move for trees, the cost for one move will be roughly the number of cells times the number of loci. For this new move, it's the sum of the number of cells and the number of loci. And since we're interested in very large number of cells, that makes a big impact in practice. Another interesting bit is that the size of the neighbor or tree that are explored are typically polynomial for moves like NNI or SPR. But here, because of multiplication, there will actually be an exponential number of neighbors that are considered.
So, I mean, this is quite different than like assuming that all of the breakpoints are IID. It's like, I don't quite understand how do you go from something that sort of, you say, okay, I have a perfect phylogeny, and then I also want to explore sub-perfect phylogenies as well?
Yeah, so basically let's say that there is just one site that is discordant that maybe has a loss. Therefore, like if we had a perfect phylogeny, the probability of the bit vector that would encode that site would be 0. Or maybe there's no configuration at all that would have a positive probability. What we have instead is that there's these latent variable X, which basically the probability will be either 1 or 0, depending on whether it's allowed by a perfect phylogeny or not. And then we have this emission mode that will then emit the actual either binary or some kind of likelihood on whether the change point, whether the copy number change for that cell between these two bins.
But you don't really have independence between sites, right? I mean, I'm not criticizing. I just want to make sure I understand.
Yes. Okay, so with the first encoding, we have the violation of independence is really bad because basically every neighbor is basically identical. Now with this new encoding, there is still independence assumptions that are broken, but they come in pairs. Basically, they correspond to pairs of sites that are linked through one event. And we're more comfortable with that kind of bad assumption because it's similar to what we do, for example, for codon by looking at each of the 3 sites. It's not great, but at least it's not as extreme as the original encoding.
Perfect. I just wanted to clarify. Thank you.
No, thanks. And this new move now is there's no miracle. So the reason we can get these good computational costs is because we're going to instantiate the location of these imputed sort of perfect phylogeny events in the tree. Okay, so that will require a non-standard tree where both cells and loci are edges in that tree. I'll talk a bit more about this soon. But first, I want to a bit sort of look at the general problem that we encountered here in the sort of practical sense. We had this new type of tree, and we want to compute posterior distribution, and we want to build a new MCMC sampler essentially, and that is correct, that gives the correct distribution asymptotically, but also is efficient enough to use that large data set. And that's part of a broader question that I've been interested for many years, which is how to implement correct and efficient posterior inference for combinatorial spaces. So in phylogenetics, this is actually a problem that arises relatively frequently for methodology developers. So for example, that occurs for joint alignment tree inference, for diversification models, gene species trees, spatial models. So if we try to be a bit more advanced in the kind of things we model, we often have this problem. So there are many existing strategies that will help you with these desiderata, but often they will help you with either correctness or efficiency. So with correctness, for example, now there are pretty good general purpose probabilistic programming language where you can only simply write the generative description of the model, and they'll automatically do inference. But the con will be that if you want to do a large phylogenetic tree, for example, using this, it might be very slow for some models. And if you want to go the efficiency route, there are lots of tools that can help you. So basically, you can program it from scratch, or you can use some libraries that will give you low-level MCMC functionality, but they will still correctness will still be challenging to achieve because we have randomized algorithms. So basically, our effort to address this practical problem is a Bayesian modeling language that we call BLANG, which is what we would like it to do is to support correct and efficient combinatorial space sampling. So it's an open source project, so you can go at this page, stat.ubc.ca/Bouchard/BLANG. That will link to the GitHub repo as well. So I'd like to thank my collaborators, Dave Kubranik, and a group of students that are starting to commit. So Sahan Hosseini, Mathieu Lepure, Kevin Chern, and Zihu Huyang. Let me just give you a little bit of a walk through what this modeling language looks like now. What we want to support first is declarative model construction. So this is a bit in the tradition of WinBugs and JAGs, if you're familiar with this kind of languages. And what we take here as a definition of a model is a collection of probability distributions, also known as laws, indexed by parameters. So that's what we would call in statistics a family. And one way to build a family is to declare, so just give a set of probabilities or conditional probabilities for each random variable. So the syntax that we use, again, is very similar to WinBugs or JAGs. And we actually try to be even closer to the mathematical notation that you'll see in statistical papers. So a basic phylogenetic model would look like this. So there's this block, laws block, which is the key part, where we declare all the conditional distribution. And on the beginning here, we give the data type for the different random variables and maybe some default values if they are unobserved. So this is the basic idea. What we want now is to push this a little bit further. And when we use a distribution like an exponential, typically in other Bayesian modeling languages, there would be a standard library that gives you a set of these. And typically, they would be written in a different language. So if you look at WinBugs or OpenBugs, they will be written in Pascal. In RevBase, they would be written in C++. In JAX, they would be written in C++. Stan in C++. Our goal was to have the standard library of Blang to be written in Blang itself. So how do we do this? Well, let's go back to how we define a model. So a model is a collection of distribution indexed by parameter. And we saw that it can be specified using conditional distribution. But now, if we stop and think, a conditional distribution can be built also from a parameterized collection of distribution by just viewing the parameter as the conditional, essentially. So basically what this means is that, so if I look at, for example, in my ID at one of these distribution, and I comment click on it to see its definition, I see that, again, I have another Blang model that tells me that an exponential is a special case of a gamma. And of course, if I go down, eventually I need to give mathematical expressions for the density of this distribution. But this is useful for teaching that the syntax stays familiar throughout the construction of these SDK. So this is a first motivation for building this language. Now we can push this idea a little bit, and often we observe that parameter, it's useful to have the parameter themselves be models or distributions. So maybe the simplest example would be like a mixture of integer valued, a mixture of integer distribution. Okay, so here the parameter is the proportion of these distribution and a list of integer distribution. And I can just write the log density of this mixture by using basically the log density of the individual components. And when I use this, I can just pass in as input for this integer distribution a list of distribution which are themselves written in Blang. And so this kind of general pattern or sort of design pattern is useful, for example, to specify branch length distribution or maybe the base measure of Edgership process and other more complex models. Now, once we have a Blang model, this the interesting bit is that as in other probabilistic programming language, this model is turned into an inference program. So basically, operationally, it just means a command line tool, if you will, that will take as input the observed data and output posterior sample of the unobserved variables. So right now, the main focus is on command line usage, but we're developing also an R interface. And the outputs are tidy CSV files, so they're easy to integrate into basically a Bayesian data science pipeline. And if you want to try that at home, if you have Oracle Java 8 and Git, you can maybe go back to these slides or look at the project webpage and try this, and you'll see the output is going to be available in a folder called results. Now, I haven't talked yet about combinatorial spaces, so let's get closer to this motivation. So another feature of this language is that it has an open type system. So if you look, for example, at our inspiration, WinBugs and JAX, you can have either integer valued or real valued random variable. And I guess the close cousin, so matrices and things like that. So with Blang, we allow object-oriented development of custom random variable data types. So in particular, combinatorial objects. So this is, for example, we have also a sample library for simple phylogenetic model. So we have an unrooted tree, which would be written in some syntax close to Java, if you will. And in some cases, just providing these objects, the BLANG might be able to do inference automatically. But realistically, we think that fully automated inference is still a bit in the future. So we'll think that for scalable models, people will often have to write their own sampler. But basically, what we want is to make this as easy as possible for them. So the way we did this is first, writing a sampler is done using a similar syntax. So it's the same language, and it's a compiled language, so it's going to give reasonable performance. And also, thanks to more advanced posterior simulation methods that I'll talk briefly soon, then the bar is a bit lower in terms of how efficiency you have to go for these MCMC samplers. Another important point is that BLANG will help you to check the correctness of your implementation. So how does that work? So this, what I mean by correctness is basically we want MCMC code, which is invariant with respect to the target distribution and also irreducible. And this seems hard because MCMC is a randomized algorithm. But surprisingly, there is some good tests that can be constructed with a bit of work. Let's just give you a flavor of what these tests look like. If, let's say, I wrote a discrete model, then BLANG provides a utility called discrete MC test, which will enumerate all the execution traces for the associated samplers and compute the posterior pi by enumerating all the possible configurations. From this, it will build an explicit transition matrix for each sampler. There should be an R here, sampler. And it will check by matrix multiplication that pi is equal to n times pi up to numerical precision. It will also check irreducibility. So in some sense, this is a final word for testing small discrete model. If the model has continuous random variable, surprisingly, there are ways to lift this to continuous space. And the basis for a bunch of tests that do this is the paper Getting It Right by Giwicki 2004. And we added a bit more new tests that are based on this idea. Now, these tests are integrated into unit tests. And so every time, for example, we commit something in the SDK, there's about 30 minutes of tests that check every distribution in the SDK. So we're pretty confident that these distributions that we provide are correct. And we also help users to that their own distributions do what they think they do. In terms of posterior inference, so one different thing compared to many other process programming language is that I will use this declarative syntax to not only build the posterior distribution, but actually a sequence of distribution. And this will be a key to more advanced inference engines that I'll talk about a little bit, non-reversible parallel tempering and sequential change of measure. Just to give you a bit of background, what I mean by a sequence of distribution, the well-known example is what's called changing the inverse temperature. So we look at the posterior as a prior proportional to the prior times a likelihood. So big L is the log likelihood, essentially. And we're going to exponentiate this likelihood to a power. And if we get, so we only do this for the likelihood so that for each intermediate distribution, it's indeed a probability distribution. And we get at the end point of that bridge two interesting bits. So one is the posterior, if beta is 1. So T is 1 over beta here. No, sorry. So T should be beta, actually. Sorry for the typo. So at one extreme, we have the posterior distribution. At the other extreme, we have the prior distribution. And an interesting bit with the prior is that with BLANG, BLANG can sample IID from the prior. So essentially, there's one distribution that's hard, and then there's one that's easy in the sense that we can get IID samples. So we use inference engine that essentially try to bridge between the two. So more on this soon. Another thing that Lang used for performance is sparsity. So samplers can be much faster if they avoid recomputing all the model components. So I showed briefly in the definition of gamma. At the end of the day, there's a bunch of these small bits that contribute to the likelihood. These are called factors. And what Blang does is it's going to use the scoping information of these factors, so which variables are accessible for each of those, to find out basically which part of the computation can be skipped when we take an MCMC move. So just to give you a bit more background, so it builds a graph where nodes are objects and edges are accessibility relationship in terms of scoping. And then if some of these will be recognized as factors contributing to the likelihood, and using simple graph algorithms that are linear time, we can build what's called a factor graph, which encodes exactly which part of the likelihood you need to compute or recompute each time you take a move. Just in terms of a bit of language details, so this Blang language is built using Xtext, which is a framework for designing programming languages. So that allowed us to take on this very big project and with low resource and in 3 years by using this framework that essentially generate a lot of language facilities for us. So for example, the syntax of the language is encoded with this a special type of grammar files, which allows mixing. So if there's parts that, for example, statements that are a bit like other languages, we can just import parts of the syntax that have been debugged already for us by this project. And so what this means is that in addition to that declarative capability that I've described, it also supports functional, generic, and object programming, static typing, just-in-time compilation, garbage collection, and so on. And there's fairly advanced IDE support that use this static type system. And at the end of the day, that runs on the JVM, so it interoperates with Java, and it's relatively fast. So just based on these advanced just-in-time compiler that Java uses now. All the engines currently use arbitrarily many cores, and in the future, we'd like to extend that to perhaps GPUs, but certainly distributed computing. In terms of workflow, you can use this in different ways. So you can use that IDE that's built on top of Eclipse that allows you to debugging, profiling, code coverage analysis, and so on. There's also a web IDE. So Eclipse in theory is multi-platform, but in practice, it can be a bit rough in the edge sometimes. Some platform, it's a bit hard to install. So if you have problem, you can contact me. I can give you access to a web IDE we're developing. And there's a command line version, which is useful to deploy large analysis. In terms of reproducibility and dissemination, so as I mentioned, or maybe I didn't mention, but the code is always fully deterministic. So even if you run the engine in multi-threaded mode, it's the output is deterministic. And we check this with unit test again. And you can also create version packages that contain model or samplers or other data types. And this versioning system is built on this tool called Maven, so it has smart dependency resolution. And at the same time, it's simple to use. There's a reasonable amount of documentation that you can find at the project address. Yeah, please give it a try if you're interested. We're very interested to get feedback and comments. So there's a natural break here. So if there are questions, I can answer a question on blank, or I can move on to a bit of the computational statistics that's underlying blank. And I can take...
Too good to be true. Like how can you code something in its own language and then have it be so fast? I guess it's because the JIT.
Yeah, so basically the miracle is Xtext in some sense. So there's they made it's now a company, so there's several people working full-time on this, and it was still a lot of work, but basically without this, that would have been completely impossible. So it's especially designed to design programming languages. So our use case is non-standard, but we try to make it so that we can leverage as much as possible. And in fact, I should say it compiles to Java, not the JVM. So it compiles to Java. It's all transparent to the user, or opaque, transparent. Anyway, the user doesn't realize it, but it goes to Java. And then it basically relies on the years of Sun and Oracle engineer optimizing the just-in-time compiler. So we're climbing on the shoulder of giants.
Cool.
So I can tell you a bit more also on the algorithms that are used to do posterior inference. So the topic here will be extensions of parallel tampering. So parallel tampering is this fairly old idea that was independently discovered in the physics and statistics literature. At a higher level, it takes as input a Markov chain Monte Carlo algorithm, and it gives you another MCMC algorithm that's often much more performant. So it works by building a bridge of distribution, as I talked earlier, and building an augmented space where we have big N independent replica of the state space. The augmented distribution is just a product of all these annealed version of the target. So at one extreme, we have the posterior. At the other extreme, we have the prior. The MCMC moves they come in two flavors. One is temperature-specific exploration. So for the chain that are not the prior, we're using MCMC kernels. And for the prior, we use IID sampling. The other type of moves is a swap proposal that looks at two adjacent chains and proposes to exchange their state and do accept-reject using metropoiesis things, MH. So the way the second step works in the naive version is to essentially for the first bit, we just do sorry, I'm going over the second bit now, how to swap proposal in more details. So we're going to look at a bunch of pairs and do accept-reject for each chain independently. The way we pick, naively, the way this is done is by picking a pair of consecutive chains, let's say I and I plus 1, and then the ratio that we get is something like this. It involves only the two parts of the target that are being swapped. Now, this parallel tampering approach works well, but it has what's called Goldilocks curse, which is this very frustrating phenomena that if you add a few parallel chain, you get benefits, so efficiency gains. But then after a point, adding more parallel chain actually becomes harmful. This is a lost opportunity because parallel tampering is actually an embarrassingly parallel MCMC algorithm, which is quite rare. You could also use distributed architecture, because a well-known trick is that instead of exchanging the states for these different machines, you can just exchange the temperature, so that annealing exponent. So it's actually a big lost opportunity that after a point, adding more parallel chain is harmful. The cause for this behavior is what's called diffusive behavior. So roughly, if you have n chain, they will require about n square steps to carry the prior to the posterior. And this is not enough to offset a parallelization gain of order n. So this is well known, this phenomenon. And currently what people do is they propose adaptive selection scheme for the number of chain n, as well as the spacings. And probably the most used recommendation is this paper by Achade, Roberts, and Rosenthal that prescribes a target acceptance probability for the swaps of 0.23, no more, no less. So when at first you'll be as you go from 1 to 2 chain, you'll be under that number, and as you add more and more chain, you'll go up. And when you get this number, stop adding parallel cores because you'll make the performance lower. Our main theoretical result, so this is joint work with my student Saf Said and collaborator George Eligianidis and Arnaud Doucet, is that Goldilocks curve disappears in the non-reversible parallel tempering regime. So the recommendation here is much nicer in terms of parallelism. So with non-reversible parallel tempering, use at least as many chains as the number of cores available. So why is this? So the simplest non-reversible parallel tempering algorithm that we can describe is something that actually exists in the physics literature and is known as the odd event swap. Okay, so how does it work? When we do the swapping, we're going to alternate between two phases. One where we do the odd swap, so we propose to swap chains starting at odd number, so 1 and 2, 3 and 4, and another phase where we do even swap, where we propose to do 2 and 3 and 4 and 5. Okay, and this trick was used sort of just as a practical way to get achieve parallelism, to be able to do these swaps in parallel, but it was not realized that it was a non-reversible move. And in fact, the recommendation for this move in the physics literature was wrong. It was still saying that you should target an acceptance rate of 0.23. As I'll show you, this is actually not true. You should use at least as many cores as possible. So here's an example of what happens. So when we compose these, we get basically that sometimes these moves are accepted and sometimes they're rejected, shown in red. So let's analyze a little bit what happens as we add more and more chains. Now, to do this, we're going to look at an equivalent representation, which is related to this idea that instead of swapping chains, states, we should swap temperature. So one way to visualize this is what happens if we follow one of the state that started, let's say, at the room temperature, and we look at the sequence of temperatures that are applied to that state over time. Okay, so we're going to call that process. So we can call it like the temperature process or the annealing parameter process, BM. Okay, so it's a vector because in theory we could follow all of these at the same time, but let's follow only one of them. Okay, so let's say BN0. So we get basically a sequence of annealing parameter that represent the path of this yellow line. What we're interested in practice is basically the probability of a round trip. So the probability that, let's simplify things for now. Let's say just the probability that we start at, let's say, the prior, and we go straight to the posterior, just like this line here. Okay, so and a round trip would be basically doing this and coming back, but perhaps with waiting time. But let's just look at the probability to go in one shot. Now, the bad news is that this process BM is complicated, so we'll have to use asymptotic analysis. Now, there were several asymptotic regimes that were explored for that process. So for example, or more generally in MCMC, I would say there's 3 types of asymptotic regime that are often taken. One is letting the number of data points go to infinity, small n, or letting the number of parameters go to infinity, p, or the running time of the algorithm, i.e. the number of Monte Carlo iteration. And here we're going to take a road less traveled, which is, at least in the MCMC literature, we're going to let the number of cores available go to infinity. And this is motivated in particular by GPUs and heavily parallel distributed setups. So specifically in the parallel tempering literature, the relevant work is, again, Achade, Roberts, and Rosenthal, which look essentially at the P regime, letting the number of parameters go to infinity, assuming there are K or D-dimensional normal distribution. And Dupuis et al. Looked at basically assuming that the MCMC is continuous time Langevin, making the swap increasingly frequent. Now here we're going to let the number of replica go to infinity. Let's assume for now they're equally spaced, but we relax that. And the intuition is that if we look at this temperature process in the reversible regime, we proved sort of the folk knowledge that this converges to diffusion. And in the non-reversible process, this converges to actually to a different object, qualitatively different, an object called a piecewise deterministic Markov process, or PDMP. So, and as you can see, the PDMP behavior seems much nicer, just goes back and forth between prior and posterior. Let's talk a little bit about what is a PDMP, very briefly. So a PDMP is a process that follows a deterministic flow. In our case, just constant velocity in the space of annealing parameters, either up or down. And then at random times, there are events. And in our case, it's just a flip of the direction. And this random time is specified by a rate parameter, lambda, which you can think about the rate of an inhomogeneous Poisson process. And the first arrival gives you the time. So it's been increasingly useful in the computational statistics literature. Here, an interesting question is, what is this rate parameter for the case of parallel tempering? And as we'll see, this actually will help us design guidelines in terms of spacings of annealing parameters. Now, we found that, we showed formally that if we look at the limit as the temperature goes to infinity, and we rescale time essentially linearly of this process B, we converge to a PDMP on the space of annealing parameter. And a very interesting bit is that we can actually compute or approximate the intensity function of basically changing the direction of this process. This rate parameter is given at a given annealing parameter T by computing the expectation of the difference in the log likelihood, where X and Y are two independent samples from the distribution at that temperature. Now, this seems complicated, but actually this is something we can estimate just from the MCMC output. This theoretical result has an important practical consequence. The main one is that if we look at the probability PM of a direct trip that started at the prior and go at the posterior, as n goes to infinity, this goes to 0 for a reversible version of parallel tempering. And for a non-reversible version, it converges to a positive constant, and I can actually compute that constant or approximate it. And our current work now is to use this characterization of the collision rate. So in order to construct if we have a finite number of cores, what should be the sequence of annealing temperature? And we have an archive coming up very soon on this. And we're also working on schemes that are based on different sequence of distributions. So for example, subsampling ideas, where instead of annealing by taking an exponent, we anneal by using less sites, or a combination of using less sites and annealing by plucking leaves, which is related to the work you guys did, Dim, Darling, and Matson, on online file SMC. Because for both of these methods, you need a sequence of distributions. So if I can take maybe another few minutes just to close the loop. I'll talk briefly about the application to single cell tree inference. So the MUL is a discrete multifurcating tree that contains L loci and C cells as edges that, or nodes that are, the cells have to be at the leaves. The MUL also has site-specific emission models. So we implemented a non-standard tree move that I mentioned briefly in Blang, which is, one way to think about this move is essentially a full conditional Gibbs sampling on that you can think about as basically you have a tree, you take a loci out of the tree, this corresponds to basically contracting an edge, and then looking at all the possible ways to add back this edge on the tree. The slight twist here is that because of multifurcation, when you insert an edge, you need to pick which subset of the children needs to be moved on the top versus the bottom of that nodes. So in theory, that's essentially visiting an exponential number of neighbors for that reason. But there's some sort of nested dynamic programming that can still look at all possible insertion point in order L plus C, a number of loci plus number of cells. And we use that correctness checking framework to check that for small trees, so trees that have less than 10 nodes, then we have exactly up to numerical precision invariance and irreducibility. And this looks small, but it's big enough to get code coverage, so we're fairly confident this move is correct. So we started playing a little bit with, there's a bit of a lag, big pictures, I think. So we started looking also at applying this to, or using parallel tempering to scale this up to large trees. So what we did is we basically compared two things. One is just MCMC on one chain, and the other one is parallel tempering using 500 chains on the largest EC2 instance in parallel computing. The data is, in this case, 679 cells from a xenograft primary triple negative breast cancer. And this is the iteration index. And here I'm just looking so far just crude statistics, so just the trace of the energy. And in parallel tempering, as you can see, does burn in much faster. But more importantly, if we look at the end of the trace, roughly more or less stationary regime, there's a big difference. So MCMC was trapped in some local maxima, and parallel tempering might also be trapped, but at least it seems to be trapped in a better optima, or maybe it explores globally by using these swaps and a feed of independent samples from the prior. So there's a few related projects that we're trying to incorporate into Blang. One of them is this other approach to use sequence of distribution, which you could call sequential change of measure. Sometimes it's just called SMC sampler, but it's a confusing terminology. Maybe annealed SMC would be a different, better term. So it's an SMC algorithm where the dimension to the target is the same at each iteration, and I can achieve a very high degree of parallelization. So we have a paper coming up in systematic biology this year, Wang and Bouchard 2019, that explore different sequence of target distributions, for example, and how it performs on computing normalization constant, which is another thing that Blang computes, since it now supports this engine as well, which you can just switch between parallel tempering or this by writing engine PT or SCM. We're also looking into incorporating this earlier work on Hamiltonian Monte Carlo for sampling parameters of rate matrices written as generalized linear models. So this modeling techniques can be used to write many existing rate matrices using one formalism. And even if the parameterization is very rich, they can be approached using a Hamiltonian Monte Carlo algorithm. So we can see this earlier paper in Bayesian analysis by my student Zhao and colleagues. And this is being ported to Blang in a project called Conifer. That's it. So I can take some questions.
Thank you very much, Alex. I feel like that was sort of a telegraph from the future. So just so I can understand, so let's say we scale it up to 500 cores.
Yeah.
Is that, I mean, so your acceptance probability goes up to 1 or something like that?
Because no. So that's a really good question. So I'm trying to go back my slides. There's this picture that, but so there was this slide that said it goes to 0 for reversible version. For non-reversible, it converges to a positive constant.
Right,
now,
right.
the catch here, the catch is that this positive constants will decrease with the dimensionality of the problem. And so basically, this function lambda is obtained by computing an expectation of a difference of 2 replica energy. So as you can imagine, if let's say the likelihood is a product, this lambda will roughly scale like square root of d. And so basically, this constant will be roughly like 1 over square root of d. So as the problem gets bigger, the probability that you go in one shot will decrease. But for a fixed problem, what this tells you is that as you add more parallel chain, the performance will always increase, but there will be a diminishing return. So at some point, you add more and more cores, and it will help a little bit. So it's not as bad as reversible, which is very frustrating. You add more core and actually make things worse. It's not that. It's just that it's diminishing return. Yeah. So that's the.
I mean, at the end of the day, like you are getting like one sample from this chain, right? I mean, you're not getting samples from. I mean, I understand that you're getting that there's lots of different temperatures, but it's not as if it's like your 500 is scaling up to get one very efficient chain.
Yeah.
Yeah.
Exactly. Well, technically, the chain that are closed, you can use important sampling to use sample from it, but that's a second order consideration. You only get like, you're right, it's only one chain at the end that will, but basically all these, there's this, here I shown you one path, but you can think about it as like there's a conveyor belt of all these chains trying to push samples from the prior. And the way I think about it is that it gives us some sort of random restarts. So once in a while, you get a sample from the prior that managed to make it all the way to the posterior, and that might lead you to visit something that's a local region that you haven't looked yet. The other thing is, so I think sort of my medium-term goal for this project is to see if there are alternative scheme where we can actually get that constant to be higher. Mm-hmm. And I think one key to this will be to use different sequence of distributions.
Very cool. I should remind people, if you want to ask a question, you can type it into the YouTube chat or tweet phyloseminar. That was a pretty dense talk. Right. So can you just say a little bit more about the eventual application? So I mean, you can get these trees. Can you just wrap it up, like related to the original question about population genetics of these different tumors?
Yeah. So basically, we the challenge is to use. So there's single cells, sets of single cells. So each of maybe I should have spend a bit more time here. So each, on this plot here, the x-axis is time in an experiment, so sort of weeks. And they correspond to one passage in generation of mouse. And so we get more and more of these sets of cells. So it's a bit like, almost like akin to a phylodynamic setup where we get more and more of these cells. And some of these experiments might also branch, where like a branch is sort of you take one sample from a mouse and you engraft it, you split it into and graft it in 2 mouse, and you submit one to treatment, the other one not. So the number of cells will keep increasing. So basically, so it's a sort of an old question of Bayesian inference of big trees, but we try to make them all as nice as possible so that it's realistic. But still, I think we'll need state-of-the-art MCMC methods to do it. So as we speak, there's more of these. There's larger and larger trees that are being constructed. It costs a lot on Azure, but it's running, and we get these large trees which are fed into a population genetics model. And yeah, so basically there actually will be a second part of this project, which will be looking at population genetics models, so starting with just simple Wright-Fisher models, and also looking at the Bayesian inference problem for these trajectories. And again, we hit, because we do it again in the Bayesian framework, we get these hard computational problems, which are posterior bridge computation for stochastic differential equation. So it seems like it's a tool that's useful to us at least, and we hope that they'll be useful for other people developing non-standard models, I guess.
But sorry if this is a stupid question. It seems like what's going on is you're inferring a posterior on trees without a fitness model, and then after you have your sample of trees, you can go back and then infer fitnesses.
Yeah, so that's a good point. So we started this looking like this, just sort of to break it into small problems. But I think in the long term, diversification models might be, or things of the flavor of diversification model might be better. So maybe the next step would be, now we look at this tree, instead of, right now we collapse it into clades. Now instead, maybe we look at the tree as the data, and then we look at fitness-aware probability distribution over trees, and to use the full tree instead of just a set of clades. We haven't started that part yet. We're still just looking at more classical Wright-Fisher model type things.
Okay, I got it. Right, so the outcome of all of this is sort of like, we think this clade is this fit and this other clade is this fit.
Yeah, exactly.
Mm-hmm. Very cool. And so are these trees that you're inferring, are they purely discrete objects?
Yeah, so that's another thing that should be improved. So we made them all as simple as possible. So the tree is fully discrete, and it has these loci imputed in them. But we could imagine maybe to feed this then into a more sophisticated model that we might even look at relaxed clock model, because now we have these cells that are at different time points. So I think there's some room there. The thing is that just for the change point themselves, there's not a crazy number of events. There's I don't know exactly what would be the order, but maybe 100 maybe for the triple negative example of these change point that we're detecting. Now, if we look after, maybe as add the point mutation to this, the point mutation would not be great at building the tree, because there's so much missing data that, in my experience, Bayesian methods will struggle with this level of missingness. But if we fix the topology and we infer branch length, these point mutation might give enough extra data that maybe we can get some reasonable posterior branch length, perhaps.
Cool. It's all very interesting. I mean, that method section for your cancer paper is going to be ridiculous to write.
I
know. Okay, well, I haven't seen any questions, but thank you very much for your talk, and we'll end the broadcast now.
Thanks so much.